In accordance with National Electrical Code Section 250.52 if a well casing composed of a metal pipe a distance away from a house's foundation fits the description given therein, it must be used as an electrode. To establish a clear and consistent approach, a boundary of 5 feet is proposed around the structure. Any electrode located within this boundary must be included in the grounding system. There are implications of creating a boundary, including increased safety. Establishing a defined boundary ensures that all accessible electrodes within a reasonable distance of the structure are utilized for grounding. This reduces the risk of electrical shock and fire hazards. Including additional electrodes improves the grounding system's overall ability to dissipate fault currents. This is crucial for protecting electrical equipment and personnel. A clear boundary eliminates any ambiguity or confusion regarding which electrodes must be considered at a structure. Inspectors can easily identify and verify the presence of electrodes within the boundary, ensuring compliance with code requirements. There are also potential challenges. In some cases, multiple electrodes may be required to achieve the necessary grounding resistance, which could increase the cost and complexity of the grounding system. Underground obstacles, such as buried utilities, may hinder the installation of electrodes within the boundary. In certain scenarios, the property line may restrict the placement of electrodes within the proposed boundary. Establishing a boundary of 5 feet around the structure for electrodes required to be included provides enhanced safety, improved grounding, and consistency in grounding practices. While potential challenges exist, the benefits outweigh the potential drawbacks. A 5-foot boundary provides a reasonable and manageable distance for including nearby electrodes, balancing safety considerations with practical limitations. A larger boundary, such as 10, 20, or 50 feet, or even the property line, introduces several complications. Firstly, the cost of compliance would increase significantly as more electrodes would need to be incorporated, potentially requiring extensive excavation and connection work. Secondly, the presence of underground utilities and property line restrictions would become more problematic, making installation difficult or impossible in some cases. Thirdly, the benefits of including electrodes beyond a reasonable proximity diminish, as the contribution to overall grounding effectiveness decreases with distance. A 20-foot boundary, for example, might encompass electrodes that are only marginally effective and could introduce additional impedance due to the longer conductor runs required to connect them. The primary purpose of a grounding electrode system is to provide a low impedance path to earth for fault currents, thereby facilitating the operation of overcurrent protective devices and minimizing the risk of electrical shock. Electrodes that are too far from the structure may not effectively contribute to this purpose and could even introduce noise or interference into the grounding system. The choice of a 5-foot boundary represents a practical compromise between maximizing grounding effectiveness and minimizing installation costs and complications. It is a distance that is close enough to capture the benefits of nearby electrodes while avoiding the pitfalls of a larger, more expansive boundary. The use of a 5-foot boundary provides a clear and consistent rule for determining which electrodes must be included in the grounding system. This reduces ambiguity and simplifies the inspection process, making it easier for inspectors to verify compliance with code requirements. This can lead to more consistent and reliable grounding practices, which ultimately enhances electrical safety. There are several factors to consider when determining the appropriate boundary for including electrodes in a grounding system. The first is soil resistivity. In areas with high soil resistivity, a larger boundary may be necessary to achieve the required grounding resistance. Conversely, in areas with low soil resistivity, a smaller boundary may suffice. The second is the size and type of structure. Larger structures may require a larger boundary to ensure adequate grounding. The third is the presence of other grounding electrodes. If there are already multiple grounding electrodes present, a smaller boundary may be sufficient. The fourth is the local electrical codes and regulations. It is important to consult with local authorities to ensure compliance with all applicable requirements. In addition to the 5-foot boundary, there are other measures that can be taken to improve the effectiveness of the grounding system. These include using larger grounding conductors, bonding all metallic components together, and installing ground fault circuit interrupters. Ground fault circuit interrupters are particularly effective at preventing electrical shock, as they can detect even small amounts of leakage current and quickly de-energize the circuit. It is important to have a qualified electrician install and maintain the grounding system to ensure that it is functioning properly. A properly installed and maintained grounding system is essential for electrical safety. By following the recommendations outlined in this proposal, it is possible to create a grounding system that provides enhanced safety, improved grounding, and consistency in grounding practices. The 5-foot boundary is a key component of this approach, providing a clear and practical rule for determining which electrodes must be included in the grounding system. The implications of not using a metal well casing as a grounding electrode when it falls within the proposed 5-foot boundary could lead to a less effective grounding system. This could result in a higher risk of electrical shock and fire hazards, as the system may not be able to adequately dissipate fault currents. Additionally, failure to comply with code requirements could result in fines or other penalties. The effectiveness of a grounding electrode is influenced by several factors, including the type of electrode, its depth, and the soil conditions. Metal well casings, when properly installed and connected, can provide a very effective grounding electrode due to their depth and contact with the earth. However, it is important to ensure that the casing is made of a suitable metal and that it is properly bonded to the grounding system. The connection between the well casing and the grounding system should be made with a listed grounding clamp and conductor. The conductor should be sized according to the requirements of the National Electrical Code. It is also important to protect the connection from corrosion. In some cases, it may be necessary to install additional grounding electrodes to achieve the required grounding resistance. The National Electrical Code specifies the requirements for grounding electrode systems. These requirements are designed to ensure that the grounding system is effective at dissipating fault currents and protecting people from electrical shock. It is important to consult with a qualified electrician to ensure that the grounding system meets all applicable requirements. The goal of a grounding system is to provide a low impedance path to earth for fault currents. This allows the overcurrent protective devices, such as circuit breakers and fuses, to quickly trip and energize the circuit, preventing electrical shock and fire hazards. A properly designed and installed grounding system is essential for electrical safety. The size of the grounding conductor is determined by the size of the service entrance conductors. The National Electrical Code provides tables that specify the minimum size of the grounding conductor based on the size of the service entrance conductors. It is important to use the correct size grounding conductor to ensure that the grounding system is effective. The grounding electrode conductor connects the grounding electrode to the equipment grounding bus in the service panel. This conductor provides a path for fault currents to flow back to the source. The equipment grounding conductors connect the metallic parts of electrical equipment to the grounding system. These conductors provide a path for fault currents to flow back to the source, allowing the overcurrent protective devices to trip. Bonding is the process of connecting all metallic components together to create a common ground potential. This helps to prevent voltage differences between metallic components, which can cause electrical shock. The National Electrical Code requires that all metallic components be bonded together. Ground fault circuit interrupters are devices that can detect even small amounts of leakage current and quickly de-energize the circuit. These devices are very effective at preventing electrical shock and are required in many locations, such as bathrooms and kitchens. Regular inspections of the grounding system are important to ensure that it is functioning properly. The grounding connections should be checked for corrosion and tightness. The grounding electrodes should be tested to ensure that they are providing adequate grounding resistance. If any problems are found, they should be corrected immediately. The location of the grounding electrodes should be clearly marked so that they can be easily located for inspection and maintenance. The grounding electrode system should be designed to withstand the effects of corrosion and other environmental factors. The grounding electrode should be installed in a location where they will be protected from damage. The grounding electrode system should be designed to provide a low impedance path to earth for fault currents under a variety of soil conditions. The grounding electrode system should be designed to minimize the risk of ground loops. Ground loops can cause noise and interference in electronic equipment. The grounding electrode system should be designed to comply with all applicable electrical codes and regulations. A properly designed and installed grounding system is essential for electrical safety. By following the recommendations outlined in this proposal, it is possible to create a grounding system that provides enhanced safety, improved grounding, and consistency in grounding practices. The 5-foot boundary is a key component of this approach, providing a clear and practical rule for determining which electrodes must be included in the grounding system. In some areas, the soil conditions may be such that a single grounding electrode is not sufficient to achieve the required grounding resistance. In these cases, it may be necessary to install multiple grounding electrodes. The grounding electrodes should be spaced at least 6 feet apart to avoid interfering with each other. The grounding electrode should be connected together with a grounding conductor. The grounding conductor should be sized according to the requirements of the National Electrical Code. The grounding electrode should be installed in a location where they will be in contact with permanent moisture. This will help to ensure that the grounding resistance remains low. In dry areas, it may be necessary to periodically water the grounding electrodes to maintain their effectiveness. The grounding electrode system should be designed to provide a low impedance path to earth for fault currents under both wet and dry conditions. The grounding electrode system should be designed to minimize the risk of corrosion. The grounding electrode should be made of a corrosion-resistant material, such as copper or stainless steel. The grounding connections should be protected from corrosion with a suitable coating or sealant. The grounding electrode system should be designed to withstand the effects of lightning strikes. Lightning strikes can cause severe damage to electrical equipment and can also pose a serious risk of electrical shock. A properly designed grounding system can help to protect against lightning strikes. The grounding electrode system should be designed to comply with all applicable lightning protection codes and regulations. The grounding electrode system should be designed to be accessible for inspection and maintenance. The grounding connections should be easily accessible for inspection and tightening. The grounding electrode should be located in a place where they can be easily inspected for corrosion and damage. The grounding electrode system should be documented with a detailed diagram showing the location of all grounding electrodes and connections. This diagram should be kept in a safe place and should be available for inspection by qualified personnel. The grounding electrode system should be regularly inspected and maintained to ensure that it is functioning properly. The grounding connections should be checked for tightness and corrosion. The grounding electrodes should be tested to ensure that they are providing adequate grounding resistance. Any problems that are found should be corrected immediately. A properly designed, installed, and maintained grounding system is essential for electrical safety. The 5-foot boundary rule provides a practical and effective means of ensuring that all accessible electrodes are utilized for grounding, reducing the risk of electrical shock and fire hazards. Implementing this proposal will enhance safety, improve grounding, and promote consistency in grounding practices. By creating a standardized approach to electrode inclusion, the overall reliability and safety of electrical systems can be significantly improved. The initial cost of implementing the 5-foot boundary rule may be offset by the long-term benefits of reduced maintenance and increased safety. The cost of installing additional electrodes, if required, is a relatively small price to pay compared to the potential cost of an electrical shock or fire. The 5-foot boundary rule is a proactive measure that can help to prevent electrical accidents and save lives. It is a valuable addition to the National Electrical Code and should be widely adopted. The importance of grounding cannot be overstated. A properly designed and installed grounding system is essential for protecting people from electrical shock and preventing electrical fires. The 5-foot boundary rule is a simple but effective way to improve the safety and reliability of electrical systems. It is a valuable tool for electricians, inspectors, and homeowners alike. By working together, we can create a safer electrical environment for everyone. The grounding electrode system plays a critical role in protecting electrical equipment from damage caused by surges and overvoltages. A properly designed grounding system can help to dissipate surge currents and prevent them from damaging sensitive electronic equipment. Surge protective devices, also known as SPD, are designed to protect electrical equipment from surges and overvoltages. SPD are typically installed at the service entrance and at branch circuits. SPD work by diverting surge currents to ground, preventing them from reaching the protected equipment. The effectiveness of SPD depends on the quality of the grounding system. A poorly grounded system will not be able to effectively dissipate surge currents, and the SPD may not be able to protect the equipment. It is important to ensure that the grounding system is properly designed and installed before installing SPD. Regular testing of the grounding system is essential to ensure that it is functioning properly. Grounding resistance testers are used to measure the resistance of the grounding system. The grounding resistance should be as low as possible, typically less than 25 ohms. If the grounding resistance is too high, it indicates that there is a problem with the grounding system. The problem should be corrected immediately to ensure that the grounding system is functioning properly. The 5-foot boundary rule is a valuable tool for ensuring that all accessible electrodes are utilized for grounding, which is essential for protecting electrical equipment from surges and overvoltages. Implementing this proposal will enhance safety, improve grounding, and promote consistency in grounding practices. By creating a standardized approach to electrode inclusion, the overall reliability and safety of electrical systems can be significantly improved. The initial cost of implementing the 5-foot boundary rule may be offset by the long-term benefits of reduced maintenance and increased safety. The cost of installing additional electrodes, if required, is a relatively small price to pay compared to the potential cost of damaged electrical equipment. The 5-foot boundary rule is a proactive measure that can help to prevent electrical damage and save money. It is a valuable addition to the National Electrical Code and should be widely adopted.